I am Ijaz Ahmed. In this lecture, we will discuss about dihedral groups and then proceed towards studying the centralizer of a group, normalizer, and the center. So we start by definition, dihedral groups. So what are these dihedral groups? These are the groups of rotations and reflections of regular polygons. So in particular, if Pn is a regular polygon with n sides, then the set of all rotations and reflections of Pn forms a group. And we call this group as a dihedral group. In mathematics, this is usually denoted by Dn, and here Dn, so here denotes the group of all rotations and reflections of a regular polygon with n sides. And this is defined as we see from the definition, that it is the group that is actually generated by two elements. One is the rotations and another is the reflection. So in fact, in the definition, we have the two generating elements x and y, and it is defined as x power I into y power j, such that x square is equal to identity and y power n is equal to identity. And furthermore, we have certain more restrictions here. We have xy is always equal to y inverse x, and I is equal to 0 and 1, and j is equal to 0, 1, 2, up to n minus 1. So this is the mathematical definition of the dihedral group. Here this x actually denotes a reflection, and this y denotes a rotation. So dihedral groups are generated by two elements, that is, one is the reflection and another is a rotation, and is defined in this way: x power I into y power j, where x satisfies to be x square equal to identity and y satisfies y power n equal to identity. And we have these restrictions here: xy is equal to y inverse x. Now, as we see that the values of I has two choices here, so this is either x power 0 or it's x power 1, and similarly j has n choices. So this clearly implies that this dihedral group Dn has two n elements. So order of Dn, this is equal to 2n. So therefore dihedral group Dn shall denote, this notation shall mean to us a dihedral group of a regular polygon with n sides, and this group has now order equal to 2n. For example, if we take suppose D4, then D4 will be defined as the group generated by rotations and reflections. It is x power I, y power j, such that x square is equal to identity, y power 4 is equal to identity, xy is equal to y inverse x, I varies from 0 to 1, and j varies from 0, 1, 2, and 3. So this means that this D4 has 8 elements, and in fact D4 by this definition means that it is a dihedral group of a square. It is a group of all rotations and reflections of a square. So suppose let's take one square here and then try to write the elements of the dihedral group D4. So let's have this square here. Let's call the vertices of this square to be A, B, C, and D. Then D4 will be a group containing 8 elements. So this is our original figure square. Then we can make a rotation of 0 degree, and then rotation of 0 degree shall be denoted by R0. And here we shall define the rotations in the anti-clockwise direction. And for the dihedral group Dn, the angle of rotation is the angle of rotation for Dn is equal to 360 divided by n. So here, therefore, in D4, the angle of rotation will be 360 divided by 4, and that will be the 90 degree. Now, first we have a 0 degree rotation in the anti-clockwise direction, and in fact, we can also define these rotations in the clockwise direction, but we shall keep it fixed that we will always have a rotation in the anti-clockwise direction. Now, the rotation of 90 degree will send A into B, B into C, C into D, and D into A, and that rotation shall be denoted by R90. And similarly, a rotation of 180 degree, that means rotating this square 2 times 90 degree. So it is the rotation of 180 degree. Then once again rotating a 180 degree figure again by 90 degree rotation, that will give us the rotation of 270 degree. And when we rotate this figure 270 degree, after making a rotation of 270, when we rotate it again by a 90 degree rotation, it will give us a rotation of 360 degree, but that shall again become the identity element. So therefore there are only 4 rotations here, and there are also 4 reflections here. Now since we have denoted in our general definition the reflection is denoted by x, so we shall have actually 4 reflections here. One will be the horizontal reflection. So let's call this red line as the horizontal axis for the horizontal reflection. Then once we have this reflection, then AB will go into DC, and this DC will go into AB. So in this way we can have this reflection, and we shall denote this element of D4 by a horizontal reflection, that is x edge. Then similarly we can define a vertical reflection. Let's call this as the vertical axis. Then along this axis, when we define the reflection, this CB will go into DA and DA will go into CB. So therefore, we shall write this element as XV. So it is the vertical reflection. Similarly, we can define a reflection along this diagonal. And along this diagonal, this when we take a reflection here, this D and B will remain fixed. A and C will be interchanged. And we shall call this reflection as XD. And then we can have one more reflection that is along this diagonal. Then here under this reflection, A and C will remain fixed, and D will be replaced by D, and B will interchange. And this reflection shall be denoted by XD dash. So these are the 8 elements of the group D4, and this D4 now forms a group under the mapping composition. Now here we can clearly see that R0 is an element of 1, element of order 1, so R0 is the identity element. And when R90, when any reflection is composed with any other reflection, it will give a reflection as the sum of those 2 rotations. If any of these 2 rotations are composed with each other, then the final rotation will be the sum of those 2 rotations. For example, if we have R90 composed with R180, that will actually give us a rotation of 90 plus 180 degree, and this will be the rotation 270 degree. And similarly, when we compose, suppose the rotation 270 degree, suppose it is composed with a rotation 270 degree, this will in total give us a rotation of 540 degree. But since a rotation of 360 is an identity rotation, so it is 360 degree plus 180. Now 360 degree rotation means a 0 degree rotation, So this 270 when composed with 270 gives a rotation of 180 degrees. So this is how we compute the elements of how we compose the elements of D4. Now we proceed towards defining the centralizer of a subset A of G. So this is a definition. Let G be a group and A be a subset of G. Then the centralizer of A is, it is actually denoted by C G of A. So it is centralizer of A in G, and this is defined as the set of those elements of G such that GA is equal to AG for all A belonging to A. So therefore we can see that the centralizer of a set A contained in G, in a group G, is the set of those elements of G that commute with all the elements of A. For example, if G is equal to D4, that is defined earlier, and suppose choose A to be the set of all rotations, it is R0, R90, R270, so and R180. There is no problem with the order of the elements. So let this be the set of all rotations from D4, and so we choose A to be a subset of D4. Then what will be the centralizer of D4? Then centralizer of the set A in D4. This will be the set of elements that commute with all these rotations. So in fact, we can clearly see from the definition that all the rotations will commute with all the other rotations. So therefore, this will contain these rotations actually R0, R90, R180, and R270. And then it can be easily checked that none of the reflections will commute with all these rotations. So therefore, in this case, the centralizer of A in D4 for this set A will be equal to A. So that is centralizer of A is equal to A. Now similarly, let's take one more example. Let G is equal to S3, and let's choose the set A. Suppose it contains just one element 1, 2. Then centralizer of the set A in G. Now we can clearly see that we have to find those elements from this symmetric group S3 that commute with the element 1, 2. And we also already know that the identity element commutes with everything, so identity will belong to the centralizer of A. And in fact, the element 1, 2 will also commute with 1, 2. So therefore, this 1, 2 also belongs to the centralizer of A. And then we can easily verify that none of the other elements of S3 will commute with the element 1, 2. So therefore, in this case, the centralizer of A will be containing these two elements, 1 and 2. Now here we note down a theorem. The centralizer of A, which is a subset of G, forms a subgroup of G. So centralizer of any subset of a group G forms a subgroup of G. Now let's proceed towards the proof. By definition, we have the centralizer of A in G. it is a set of elements in G such that this GA is equal to AG for all A in for all A in the set A. Now first we need to show that the centralizer is a non-empty set because every group is a non-empty set first. So clearly identity element. So whatever is this group G, clearly the identity element of G is in centralizer of A in G. So this means whatever is the set A, the centralizer of A in G is always a non-empty set. So now let's choose two elements. Now let G and H belong to the centralizer of A. So this implies GA is equal to AG and HA is equal to AH for all A belongs to A. And this comes from the definition of the centralizer. So once we have HA is equal to AH, then this gives, then pre-multiplying this by H inverse and also post-multiplying by H inverse to this equation, this gives us AH inverse is equal to H inverse of A. So this implies H inverse belongs to the centralizer of A. So whenever we have an element H in the centralizer of A, then H inverse also belongs to the centralizer of A. Similarly, we can see that when G belongs to the centralizer of A, G inverse will also belong to the centralizer of A. Now in order to prove that the centralizer of A is a subgroup of G, we shall prove that GH inverse should belong to the centralizer of A. Now, what about GH inverse of A? So if GH inverse of A happens to be equal to A, then it means that we actually need to prove that GH inverse of A is equal to so actually we need to compute GH inverse of A into GH inverse whole inverse, and this should be equal to A, and this will mean that uh, this GH inverse also commutes with every element of A. Now by definition this is equal to GH inverse then A, and by the reversal law of inverse this is equal to H G inverse. Now here we can use the associativity. This is equal to G H inverse AH G inverse, and by definition since HA is equal to AH, it means that H inverse AH will be equal to A, so this actually gives us G A G inverse, and again using the associativity this actually gives G A G inverse, since G also commutes with A, so therefore G A G inverse will again be equal to A. So therefore the element GH inverse also commutes with A. So whenever we have an element that commutes with every element of A, this implies that GH inverse belongs to the centralizer of A. So therefore we had chosen two elements G and H from the centralizer of A, and we see here that GH inverse also belongs to the centralizer of A. So therefore centralizer of A is a subgroup. Now we proceed towards one more definition, that is the center of a group. Center of a group. So we define the center. The center of a group G is the set of those elements of G that that commute with every element of G. So in terms of the centralizer, so that is the center of a group is actually denoted by Z of G. So this can be defined as the centralizer of G in G. So if we choose the set A as the whole set G, then the centralizer of that A will be the center of G. So this is equal to the set of elements G belonging to G, such that GH is equal to HG for all H belongs to G. So center of a group is the set of those elements of their group that commute with all the elements of G. For example, center of D4 is the set of elements R0 and R180. And this can be verified by the direct computation. And since R0 always commutes with all the elements, and then it can be checked that R180 also commutes with all the elements of D4. And so the center of D4 is the set of elements R0 and R180. And similarly, the center of S3, there is only the identity element in S3 that commutes with all the elements of S3. So here we have one clear observation. There is a clear observation. If G is an abelian group, G is an abelian group, then center of G is the whole group G. Now let's take one more example here for the center. Let's take the group Q4, the group of quaternions. It contains the elements 1, minus 1, I, minus I, J, minus J, K, and minus K. Now there are certain more restrictions here. In fact, there is I square is equal to J square is equal to K square, and this is equal to minus 1. Ij is equal to K, Jk is equal to I, and Ki is equal to J. And similarly, when we take the reverse, Ji, this will be equal to minus K, Kj is equal to minus I, and similarly, Ik is equal to minus J. So in fact, these things can be remembered by writing them on a circle. So let's write I here, let's write J here, and let's write K here. Then I into J will be equal to K, J into K is equal to I, and K into I is equal to J. And similarly, when we take the product in the reverse order, that is J into I, that's minus K, and so on. This is the group of quaternions, and here the center of Q4. Center of Q4 is the elements 1 and minus 1. Now we proceed towards one more definition, that is normalizer. Normalizer of A contained in a group G. So this normalizer of A in G is the set G, A, G inverse. It is a set of elements G belonging to G such that GA G inverse is equal to E. For example, suppose our set G group G is equal to D4 and our A is the set of all rotations that we are taking the same example in the definition of the centralizer in the example of a centralizer. So we shall take the same example here for finding the normalizer of this set A. So this is our set A, which is the set of all rotations of S square. Then we need to compute the set G A G inverse, and this should be equal to A, and we have to take course of those G's that satisfy this equation. Then G A G inverse is equal to A, and we have to find these G's. We can clearly look from the definition of the dihedral group D4 that all these rotations R0, R90, R180, and R270 will always satisfy G A G inverse is equal to A. So the normalizer of this A always contains A. Now we proceed towards choosing some reflection. So let uh, S be a reflection. Let S be a reflection in D4. Then we have to compute S A S inverse, and this should be equal to A. So this SAS inverse, by definition, this is equal to S R0 S inverse, then S R90 S inverse, then we have S R180 S inverse, and S R270 S inverse. Then this can clearly be seen that this is actually equal to, so this first is equal to R0, and this second will be equal to R270, and this can be done from the direct computations. Whatever is this S, then SR90 S inverse will be equal to R270, and this thing will be equal to R180, and this will be equal to R90. So this means that, but this is the set A. So finally what we conclude is that is, so thus a reflection belongs to normalizer of A and G, where A is this set of earth rotations. And we can clearly see that this normalizer of A also defines a subgroup of G, and that can be easily proved as we had proved the centralizer of A is a subgroup of G. On the similar note, we can also prove that the normalizer of A is always a subgroup of G. Now, since from these computations we have seen that this S, which is a reflection, it belongs to the normalizer of A, and this A already contains a reflection. Therefore, this normalizer of A contains at least one reflection and in fact all the rotations. So thus X and Y both belong to the normalizer of A. So here this X is actually, we mean by writing this that X is a reflection. That is, reflection belongs to the normalizer of a group, normalizer of this A, and in fact the rotation also belongs to it. So when both reflection and the rotation belongs to the normalizer of this A, and since this normalizer of a group is a subgroup of G, so by closure of normalizer of A, we have x power I, y power j must belong to the normalizer of A in G. Now, since this normalizer of A is a subgroup, so whenever we have a reflection there, when we have already a rotation there, and we have proved that there is also a reflection inside this set, so this x power I and y power j will belong to the normalizer of A, being by the closure property of the normalizer of this A. But when x power I, y power j belongs to Ng of A for all I and j, this implies this D4 is actually contained in the normalizer of A, because this, when x power I, y power j is computed for all I and j, that actually gives the whole group D4. So this means that D4 is wholly contained in the normalizer of A, this implies this implies D4 is equal to normalizer of A. So therefore, when A is the set of all rotations from D4, then the normalizer of that A will be the whole set D4. So therefore, since we have taken this example of D4 for taking the example of a normalizer of a set A, and we have also computed the center of this D4, and we have also computed the centralizer of this set A from D4. So we conclude here, it can be easily seen that the centralizer, the center of group is always a subset of the centralizer of G, centralizer of A in G. And the centralizer can be easily obtained to be the subset of the normalizer of G, normalizer of A in G. So whatever is our set A, then center of a group is always contained in the centralizer of every subset of G, and the centralizer of every subset of G is always contained in the normalizer of every subset of G. But here, and we have taken here an example, if G is equal to D4, and we have taken the set R A equal to R0, R90, R180, and R270, then we had seen that the center of G contains two elements, but the centralizer of this A contains four elements. So here we see that the center is contained in the centralizer, but it is properly contained. So it is properly contained in the centralizer. And since the normalizer of the same set is the whole D4, so this is properly contained in the normalizer of A. So therefore, actually what we want to conclude here is that it is not always necessary. It is actually always true. Center is contained in centralizer, and centralizer is always contained in normalizer. But there can be a strict inclusion also. So with this thing, we conclude this lecture now.